Okay, and now we're going to pick up and carry on where we left off. This time we're going to prove a very pivotal property of matrices and determinants. And it is the following, property 1.41 in the text by Shilov. And it says, in certain words, let A be a square matrix, then the determinant of A is equal to the determinant of A transpose. Now I got to warn you before we prove this, it is very terse and very difficult to follow if you don't have experience. So I want to warn you of that. If you get confused, I strongly encourage you stop it, rewind it, think about it, puzzle over it. It's not going to be something that you're just going to be able to watch from start to finish and go, oh yeah, it's not going to happen. So just want to get that warning out of the way. You're going to have a bad time if you do it that way. Just saying. Okay, but here we go. Here's the proof. Let A be equal to a matrix whose entries are of the form A sub ij, and let it be a n by n, or square, matrix. Then A transpose, which is the matrix whose entries are of the form A sub ji, is also an n by n, or square, matrix. By definition, the determinant of A, which is equal to that nasty mess of a sum, where alpha ranges over all possible permutations in the set 1 through n. Now, you should realize by now, if you don't understand the definition of the determinant, it's probably going to be pretty rough going making sense of this proof. So if you don't know the definition of the determinant, go ahead and watch a previous video that I uploaded on the definition of the determinant. There's going to be more where this came from, so if this looks awful and hard to follow already, oh man, you're going to have a great time. Awful time. Anyways, so that's just the definition of the determinant. It's a sum of that form over all possible permutations in the set 1 through n. That's it. Since A transpose is the matrix whose entries are A sub ji instead of ij, right? We've just switched rows and columns. Then the determinant of A transpose is equal to that nasty mess of a sum, which is a determinant. Okay, and I've changed the permutation. I'm not using alpha, I'm using beta to differentiate it from the permutation I used in the determinant of A. Okay, so where beta ranges over all possible permutations on the set 1 through n. And also note, if you haven't noticed, that permutation beta is occupying a different subscript than the permutation alpha was, and there is an explanation forthcoming here. To see why this is true, define A sub ij transpose to be equal to A sub ji. So we're just coming up with another slightly different shorthand here. Then A transpose is equal to the matrix whose entries are of the form A sub ji instead of ij, which is equal to the matrix whose entries are of the form A sub ij transpose. Okay? I've just substituted, that's all. I'm just using substitution. I'm using my new notation that I just introduced mid-proof. Okay, and the determinant of A transpose is equal to the determinant of the matrix whose entries are of the form A sub ij transpose, using my new notation, which is equal to the following nasty sum, and that is simply the definition of the determinant. See? The definition of the determinant, right there. That's it. Okay. But now I've just used substitution on the far right equation there. Instead of writing all those entries with the transposes on them, I've just substituted it. I've used substitution. Since A sub ij transpose is just A sub ji, well, I've just written it another way on the far right, which happens to match what I was using in the previous paragraph. So I've just explained why I can write it that way. That's it. So now where were we? We wish to show that the determinant of A and the determinant of A transpose contain all of the same terms, differentiating at most by their sign, we will show later that corresponding terms must also have the same sign, and then therefore they're the same. And this is how we're eventually going to show that the determinant of A is the same thing as the determinant of A transpose. But we've still got a ways to go yet. Okay, moving on. So we have the determinant of A is equal to that nasty sum, and the determinant of A transpose is equal to that other nasty sum. We've established that just now. Okay, we claim that for each permutation alpha on the set 1 through n to the set 1 through n, there exists another permutation beta that goes from the set 1 through n to the set 1 through n, such that, okay, these products of the entries in the matrix A are equal to the products of the entries in A transpose, right? Where I've got on one side I'm using alpha, and on the other side I'm saying, well, they're equal to the product using the beta permutation. There is some permutation beta that will make that work. Basically what I'm doing is I'm going to show that if you look at the determinant of A and you take a term there is some matching term on the determinant of A transpose, right? I can say, here's a term, oh, there's one for the determinant of A transpose, they match. And I can do that, as I will show, for every term. But yeah, here we go. And this is what we're talking about here. All right. To prove this, we will construct beta according to alpha. Start by examining the factor A sub alpha of 1, 1. So just check that one out. That's it. Right? Since alpha of 1 is in the set 1 through n, then there exists a p sub 1 in the set 1 through n such that alpha of 1 is equal to p sub 1. That's basically just a fancy way of saying alpha of 1 is in that set 1 through n, so let's give it a label and call it p sub 1. There you go. Alright, now here's the key. Define beta of p sub 1 to be equal to 1. Okay, so alpha takes 1, maps it to p sub 1, beta takes p sub 1, maps it back to 1. If that's starting to sound like an inverse function, you're right, it is, but we'll get to that later. Then we must have A sub alpha of 1, 1 equal to A sub p sub 1 beta of p sub 1. Okay, and this is where I'm getting it from. I'm just substituting. Since alpha of 1 is equal to p sub 1, then I'll write p sub 1 instead of alpha of 1. And since beta of p sub 1 is equal to 1, well then instead of writing 1, I can write beta of p sub 1 if I want, which is what I did. Okay? Now consider the second factor. Okay? A sub alpha of 2, 2. Okay? Similarly, alpha of 2 is equal to p sub 2 for some p sub 2 in the set 1 through n. And we may define beta of p sub 2 equal to 2. This yields A sub alpha of 2, 2 equal to A sub p sub 2 beta of p sub 2. Okay, and we got this just exactly in the same way that we got the last one. So if you could see the pattern here where we're going with this, that'd be great. Okay? Alright, we may proceed in this fashion until we have exhausted all images alpha of I, and we have alpha of I is equal to p sub I, beta of p sub I is equal to I, and A sub alpha of I is equal to A sub p sub I, beta of p sub I, for all I in the set 1 through n. You start to see what I was talking about? This is crazy, this proof. But I'm sure you'll rise to the occasion. Thus, for every term, that's a product, right, that came from the determinant of A, in the determinant of A, there is a matching term in the determinant of A transpose. Okay? And I've just shown that just by constructing this permutation beta in such a way. So I've proven that you can choose a term in the determinant of A and then I will show you a term in the determinant of A transpose that matches it. Okay, so we will now show that these terms must have matching signs. In other words, they're the same. Okay. So first let's collect a couple of points that are important here that we've already established. First is that the determinant of A is that nasty sum, and the determinant of A transpose is that other nasty sum. If that wasn't clear, let's just get that out in the open air right now. Secondly, the second point is, for every permutation alpha on the set 1 through n, there exists a permutation beta on the set 1 through n such that alpha of I is equal to p sub I, beta of p sub I is equal to I, and a sub alpha of I is equal to a sub p sub I, beta of p sub I, for all I in the set 1 through n. Okay? Since alpha of I is equal to p sub I, and we have defined beta of p sub I equal to I, for all I in the set 1 through n, then alpha of beta of p sub I is equal to alpha of I, which is equal to p sub I. And beta of alpha of I is equal to beta of p sub I, which is just equal to I, for all I in the set 1 through n. Okay, now let's take a look at that first one. How did I get this? Just using substitution, basically. Since beta of p sub I is equal to I, I'll just write I instead of beta of p sub I. Okay? And since alpha of I is equal to p sub I, I'll just write p sub I. Okay, so thus alpha of beta of p sub I is just p sub I. Alright? Now the next one, how did I get that? The same way. Since alpha of I is just p sub I, then I'll just write p sub I instead of alpha of I. And since beta of p sub I is just I, then I'll just write I instead of beta of p sub I. It's that simple. Okay, moving on here. And here's the important part. Observe that alpha and beta are inverse permutations. Right? That's what I've just shown here. Alpha undoes beta. And so when you compose alpha with beta of p sub I, you just get p sub I. Similarly, when you compose beta with alpha of I, you just get I. They undo each other. They're inverse permutations. Since inverse permutations have the same parity, that's another thing that we've proved in the past, then these powers of -1, right, they must be equal. They must be equal. Right? So if the one permutation is odd, then so is the other. If the one permutation, if alpha is even, so is beta, right? And so therefore, this -1 to the power of the number of inversions in the permutation, they're going to be the same. It's either going to be plus or minus 1, and they're going to match exactly. So therefore, corresponding terms from determinant A and determinant A transpose have the same sign. So since the terms in each of the determinants, there are matching terms, and those matching terms have the same sign, then guess what? That means that the determinants are the same. So yeah, QED. Alright, so that was horrible. Next time, we'll do something easier, and that's a property 1.42, also in the book, and I believe Sharlov refers to it as the Antisymmetry Property. And it goes like this. Let A be a square matrix, and let B be a matrix that is formed from A by interchanging two columns or rows. Then the determinant of A is going to be the negative of the determinant of B. So basically what that's saying is when you interchange two rows or columns, you just change the sign of the determinant. That's what you do. And that one should be a little bit easier. I think that one's also kind of a gnarly proof. But basically from this point on forward for a little while, I guess, the proofs are going to be less gnarly than the one you just saw. And this property here, that the determinant of A is equal to the determinant of A transpose, is really important. A lot of what you do with determinants from here on will rely on these elementary properties that we're going through. So, next time.